A 1982 paper by Hans Rosendahl and Samuel Shaw established a correlation between the maximum sustained surface wind speeds to the minimum sea level pressure in central North Pacific cyclones. Use the following data below to test this result. All right, so we have a group of storms here, and the minimum sea level pressure recorded for each of these storms is provided as our independent variable. And then the surface wind speed that's also measured here is also recorded. Okay, so we want to know if this data is correlated. So let's find the correlation coefficient. Well, to do that, we will use the calculator here. And it doesn't really matter if you're using a TI-84 or TI-83 or if you're using the online stats calculator. They all work basically the same in this respect. So the first thing that we need to do is to input the data into a list. So we'll go into our list editor, and the X data will go into L1. So I'll type that in as quickly as I can for you. 1009 and 1014. All right, and then that last value is from a previous data set. I'll just remove it. And then the Y values, so the output values here, those go in L2. And again, I'll just type those in as quickly as I can. Now, in order to do linear regression, what we need to do is first hit the stat key again, but do be careful. There is under the calc menu, there's a linear regression feature called just linreg ax plus b. It's a very basic form of linear regression. It doesn't do everything that we need it to do for this class. So just skip on past that and get into the tests submenu, because we're always going to be doing hypothesis testing with respect to linear regression. And if you scroll down, you will eventually arrive at the function linreg t-test, and that's what you want. And it will give you basically all the values for A through E here. So just make sure your X data is in L1, your Y data is in L2, and you're doing a hypothesis test where the alternative hypothesis is not equal to 0. So it's a two-tailed test. And that's always going to be the case. So you can even see right here it says to use a not equal to 0. All right, so let's run this. The correlation coefficient, that is at the bottom, and it's the value R. So in this case, it's negative 0.933. So R equals negative 0.933. That's all we need there. Now, that is a very high, in absolute value, it's very close to 1. So that's a very high correlation. So we've got a pretty good chance that this data is correlated, but we're not certain until we've actually done a hypothesis test. And the hypothesis test is doing a hypothesis of the form where the null hypothesis is rho equals 0, and the alternative is that rho is not equal to 0. And what that means is rho is the population correlation coefficient. R is the sample correlation coefficient. So what we want to know is the population correlation coefficient 0, meaning that there is no statistically significant correlation, or is it something other than 0? That's what we're trying to figure out. So to do that, we calculate a p-value. And thankfully, still inside this same function is a p-value. It's 0.021 in this case. So the p-value of 0.021 tells me just basically how strong that relationship is. All right, so, but in a hypothesis test, you have to have some level of significance. All right, so then that's what's actually being asked here in the next question. With a 5% level of significance, is there a strong indicator of a linear correlation between these variables? Well, if we compare the p-value, which is 2.1%, to the level of significance of 5%, and p is low, so the null must go. And if the null must go, what we're saying is this statement right here is not true, leaving the other to be true. So the other one is that the population correlation coefficient is non-zero. We're supporting that, which means that there is a correlation between the data sets. So yes, there is a statistically significant correlation between these variables. And when there is, we can actually, it makes sense to compute the regression line. We can compute a regression line for every data set. It doesn't really matter. But for it to be meaningful, we have to make sure that there is a statistically significant correlation. Now, to get the regression line, we just look right back into our output screen. And if you'll see here at the top, it says y equals a plus bx. A is the y-intercept of a line equation, and b is the slope. Now, slope is usually m in like a algebra class, but that's okay. It's the meaning of the variable rather than the name of the variable. So it's the thing multiplied by x. So we can write this regression line as y equals negative 1.39 times x and plus 1469.5. Okay, now just be really careful with rounding because however many decimals you take these to, it can be very sensitive to how you choose that rounding. And you might get the regression line equation correct. It could just be within a certain amount of tolerance of being correct, but then miss part E when you're asked to use that line to make a prediction. So just be really careful with your rounding. On your exams, just make sure you write little breadcrumbs as where each piece of data came from, because if you have some value that's different from what I'm expecting on my answer key, but you have all the supporting evidence as to where your values came from, and I can just tell real quick that the only thing different is how many decimal places you chose in part D, well, that's no big deal. Of course, I'm going to give you full credit. So just give breadcrumbs as to where your values, where you got your values. All right, so anyway, part E says, new data has just arrived indicating that the minimum sea level pressure for a storm is 955 millibars. So if that's the case, we want to know what the maximum sustained wind speed is actually going to be here. So x is the minimum sea level pressure. So I'm going to substitute x for that minimum sea level pressure, which is 955. So I'm putting that into my line equation, and then it's going to give me a y value back out. And so it's going to make a prediction on the y data, which is actually the surfaced wind speed. So this prediction is going to be, let's see here, negative 1.39 times 955 plus 1469.5. So 142.05. And so we'd probably just say 142 miles per hour. But that's how we go about doing a full good example of linear regression.